Good morning, steam power plants class. Here we go. The first of the recorded videos for this week. I'm going to do about 30 or 35, 40 minutes now. And I have found another very good video that I'll send you the link to. So it's a little over an hour. So the combination of these two will more than make up for one of our two classes this week. Okay, so this is the second slide in the scan material on boilers. I was looking at this, but this one laid out and showed some of the various sections of the boiler, maybe a little better than that first one. So I'm going to talk from this today. And so I think we've worked our way through the water paths as the air or the water enters the boiler in the economizer. It's preheated, goes to the drum to the water walls, creates some steam, goes back to the steam drum, gets separated. It's the primary superheater, then it goes to the secondary superheater, and then it goes out to the turbines, comes back, goes to the reheaters. We've got some temperators along the way, goes back to the IP turbine, LP turbine, condenser, and then back through the steam cycle, through all the feed water heaters, extractions and all that stuff. So we've done that. So now I'm going to talk a little bit about some of the airflows through the boiler. And fortunately, I don't have a diagram that shows it really very clearly. There's lots of ducts and passages that are just not clearly indicated. This is the best figure I have, I think, to show it. So we'll talk from it. And, there'll be some of the details that you just probably won't quite get here. But that's okay. We can refer back to the steam book that has, Lord knows, everything. So at any rate, the FD fan, forced draft, means it's blowing into the boiler, is back here. I don't know why this little do-jigger keeps showing up. I hate it, but it does. Anyway, I guess I won't use that pointer. But we see where the air from the forced draft fan enters. It is ducted into the boiler. The pressurization in the furnace is controlled by the balance between the capacity on the FD fan that's blowing in and the ID fan that's sucking out. And then the ID fan is basically pretty close to the stack, and it's blowing up the stack, but it's on the suction side, it's pulling stuff out of the boiler, whereas the FD fan is pushing into the boiler. So capacity control on those fans is very important to make sure that we keep our pressurization about correct on the boiler. Okay, so the air is blown in from the FD fan, and then we see down at the bottom of the boiler, we see a pulverizer, and then we see a primary air fan. So, I guess the other thing I didn't mention is from the FD fan, we are pushing through the air heater that you see. It's a rotary type air heater. We have hot flue gases going on one side of it, and the forced draft fan air going on the other side of it to pick up heat before we go into the boiler. After we preheat, then we come down, and a portion of the air from the FD fan is pulled off by the primary air fan and is blown through the pulverizer. And the pulverizer then has coal falling in from the coal bunker. You see over there on the left-hand side, from the bunker to the coal feeder. It falls down into the pulverizer, where it is ground up to a consistency of face powder. That hot air, 400 or 500 degrees, or even potentially hotter, from the air heater through the primary fan, then is blown through the pulverizers to transport the pulverized coal through the coal pipes into the burners, on the side of the burners. side of the boiler, and then from there it's blown out into the fireball where it is combusted. So that's one path. The air that does not get pulled off by the primary fan, part of it goes to feed the wind boxes, which supply additional air directly into the fireball. And then we have some air that goes to the secondary air duct that then is staged in further downstream into the combustion zone. So the idea here to limit NOx formation, NOx, which is oxides of nitrogen, NO, NO2, NO3, and there's probably some other nitrogen compounds in there, but basically they all just kind of lump together and called NOx. And that's, back in the day, that was the brown LA haze that the song talked about, which the catalytic converters on the automobiles and the cleanup equipment, the ammonia injection at the power plants has gone a long way to take the NOx out of the air that we breathe. So power plant does a good job on controlling NOx. But the theory is that there's really two main sources of NOx in the combustion world that affect utilities. One is called thermal NOx, and thermal NOx is caused by the dissociation at high temperature. An N2 molecule will split apart into two ends, and a single end molecule is extremely reactive, and it's wanting to mate up with something and form some kind of a compound. So if it comes up against an oxygen, it's going to make some sort of a NOx molecule that then is going to be pollution if we don't somehow get it out of the gas flow. The other is bound nitrogen in the fuel. Coal has a certain fairly small percentage, but it still has some nitrogen bound up in there. And when that combusts in the flame, when that coal particles burning, that combustion zone can create what they call fuel NOx. So there's fuel NOx, there's thermal NOx, and there's also a small category called prompt NOx that we'll let the steam book tell you about. It's a fairly small contributor, but there is that third category. I'm not going to go into that in this recording. Okay, so the idea is to stage the combustion. You know, if you throw all of the air that you really need into the furnace at one location, you really increase the temperature of the fireball. So temperature is good in terms of efficiency, but temperature is bad in terms of NOx. And like I've told you today, it's the environmental aspects are the tail wagging the dog for sure. And so the low NOx burners and furnace designs are to do what they call stage combustion, which is to stretch out the addition of oxygen to the point that we finally do burn the fuel pretty much, but we do it in a lower temperature environment, which limits the NOx formation. So we don't have as much to clean up after we get the gases out of the boiler. So you have multiple ports in the boiler that are supplying air well beyond that it comes in with a primary fan through the coal pipes, and then the wind box, the injecting air directly into the area where the fireball is probably the hottest, and then we have secondary and overfire air and all kinds of different airports on further downstream. So that part is fairly complicated, and these diagrams don't really show it justice. Okay, so once we get the air into the boiler, it's used in combustion. Hopefully we have good mixing, and so that the oxygen and the air that we get in there is mixed well and is in a position to support the combustion of the coal. residence time of those coal particles is really not all that long. They move pretty quickly through that furnace, and so we need to get everything combusted. We need to get the carbon burned out as quickly as possible to make sure that it doesn't wind up as unburned carbon or LOI or loss on ignition. That's carbon in the ash that we separate out at the precipitators. Okay, so from the furnace, I guess I'll try this again. If you can see that moving around a little bit. So in the furnace, this is where the combustion is taking place. And let me go up just a tad higher here. Okay, so we call this portion of the boiler the furnace, and once we exit here sideways, this is the convection pass. So the convection pass goes horizontal and then downward across more heat exchangers, and then eventually over here and down through the air heater, and then we exit and go for all of the gas cleanup equipment, which would be for NOx, SOx, the mostly SO2, sulfur compounds, and then the particulates. And in those two, removing the NOx and SOx, we also do a pretty good job of knocking down the mercury and the heavy metals. Some of those get pulled out as well. So, you know, it's pretty good, except for, as I call it, the dreaded gas, the CO2, which is what this whole contraption is designed to create. It's designed to basically burn carbon and coal to CO2. So just the way it is. Okay, so as the gases exit the furnace, this is our hottest gases. It's good to have, a lot of boilers have what they call an FEGT, a furnace exit gas temperature, because that's a good indication of how the combustion is going at different loads to the operators. And it's trying to measure that temperature exiting the furnace into the secondary superheater. It's a challenging environment to maintain thermocouples and temperature sensors, and so most boilers have them. Sometimes they have a hard time keeping them in service, but it's a very good indicator. It's an FEGT, furnace exit gas temperature sensor. Okay, so that's going to measure the temperature into the secondary superheater. And so, you know, as we go across all these heat exchangers, the gas is going to cool down. So this is the last heat exchanger that the main steam sees before it's going to the turbine. So it sees the hottest flue gas. And so in this diagram, we're also showing typical soot blower locations. We haven't talked much about soot blowers, but ash, all these little ash particles can accumulate on the tubes. We'll talk more about coal characteristics, but different coals have different ash softening temperatures and melting temperatures, and they talk about ash fusion temperatures. And if you get, if that coal has an ash softening temperature that is low, and you get to that temperature, then it makes those ash particles sticky, kind of gummy, and that'll slag up something terrible. So you got to be careful in purchasing the coal and knowing the temperature characteristics of your boiler to make sure that you purchase appropriate coal, or you can slag the heck out of a boiler in a very short period of time, because there's a lot of ash passing through the system. Okay, so we our hottest flue gases pass across the secondary superheater. There's soot blowers involved. We're showing reheat superheaters. There could be more than one. This could be a secondary. We could have a primary back down here. Just depends on how much heat transfer area and the design on the boiler. But we're going laterally through the convection pass. The convection pass is lined with tubes. to not only to suck up heat, but to cool the convection pass itself, the structure of it. We're coming on across. We come down. We're the temperatures along the way. We've talked about those, but of course that's in the steam side. So this flue gas is just passing across these various tubes, and the enclosure is lined with tubes as well. So then we come down across additional. We got the primary superheater, and then we come down across the economizer. So again, we're sucking heat out of these gases, trying to be as efficient as possible. We come down, we cut over and go through the rotary air heater, where we've got the blast from the combustion air coming in from the forced draft fan. On one side of this is the thing that rotates around, and half of it has the hot flue gas on one side, and the other half has the combustion air. And they just, there's all kinds of metal and heat transfer surface in there that gets hot, rotates around to the cold side. This thing just runs around in a circle. These air heaters, they have seals on them, but the seals are not real good, and so we can leak air from the high pressure side is on the combustion air coming in, because that's on the blast of the FD fan. The flue gas side is negative in pressure because it's being sucked out by the ID fan. So if the seals are not good, we will lose combustion air, and it will actually leak into the flue gas. So one way you can determine the amount of leakage is to measure the percent oxygen in the flue gas before and after the air heater. So if you have a big increase in oxygen, that tells you that your seals are bad on the air heater, and that's a significant loss mechanism. So that would need to be addressed. What will happen if it gets bad enough is you simply can't get enough air into your furnace because it's leaking into the flue gas as it passes through the air heater. So you can tell that by the amount of oxygen in the flue gas. You can tell it because you can't get the unit to full capacity. You can also look at the temperature drop across the air heater. So if it's not right, because some of that cold air is just leaking directly into the gas, you can also probably try to look at pressure drops downstream to see that you have much more flow coming into that ID stream than it's really designed to handle. So then, like I said, from here we go to the gas cleanup. I think that's pretty good. Let me go pull down here. I think we've got some slides that show some of that. This is actually the smaller unit at Kingston. This is what the diagram, those boilers looks like. We can see, take a quick look at this. So you see the regenerative air heater here. So we've got coal on this side, pulverizers. Here's our FD fan. So it's blowing here through the air heater, and then we come into the boiler. Let's see, I don't see a primary air fan, hot air duct. So yeah, so we're ducting over here to the pulverizers. They're all similar. I mean, you know, different size. This is a fairly small unit, so I'm not seeing a primary air fan. I don't know if they have one or whether they do it all off of the FD fan here. But at any rate, you see the, you know, we've got our coal pipes and we're feeding our burners, and, you know, we've got airflow into the boiler at different locations. You see the, as the furnace, as the gases come out, are different superheaters, reheaters, all that, economizer. So after you start looking at these things, there's the steam drum up on top. One thing I didn't mention, I don't think, is these boilers are all suspended from the ceiling. So the entire structure is suspended from the roof up here. And this is to allow this thing to grow when you heat it up. So the overall height of this boiler, as far as all of the tubes and everything that's suspended from the ceiling, will grow by, I don't know, a foot, something like that, between the hot condition and the cold condition. So you can't just constrain all of this, because when you heat up that metal, it's going to expand, and they're tall enough that you get a significant amount of expansion. It will simply buckle. If you constrained it on both ends, it would simply, when it got hot, it would buckle the tubes, or it would rip something loose. Just whatever the weakest link in the system is would go. So all of these utility boilers are suspended from the ceiling so that they can allow for the thermal expansion to take place. Let's go down and see what else we got here. These are the larger boilers at Kingston. So look at that. Here we go. This is showing a little bit of the cleanup stuff. Yeah, this is pretty good. So the SCR is for NOx elimination or reduction. Selective catalytic reduction. Usually use some kind of an ammonia. Urea can be used because it will be transformed into ammonia in the reaction. But that's, so as we exit the furnace, we go through the SCR, and actually we go through the SCR before the air heater. So we've not shown that before. So actually we come out, we go through the SCR, then we go through the air heater, because this needs to be done at fairly high temperature. I think it's 500 to 700 degrees, something like that, maybe a little hotter. But there's a particular temperature ranges where these reactions work best. We get to the chapters on the steam book. You'll get that in depth and detail. And so this is then the rotary air heater. So we go through that. And then we go for particulate collection, electrostatic precipitator or fabric filter. The bigger units are electrostatic precipitators. We'll talk a little more about those. How those operate is they have these electrodes, long electrode wires, and they induce a significantly high voltage. And the voltage basically attracts the ash particles. There's a charging mechanism somehow in there. And anyway, the ash particles collect on the electrodes, and then every hour or so, whatever the timing frequency is, it's done automatically. They switch off a section of the electrodes, and a big hammer comes down and wraps the top of the frame, and it knocks the ash off, and the ash falls down into collection bins at the bottom and then gets trucked away. So we're constantly cleaning different sections of the precipitator by doing that. So, taking the voltage off of the system, shutting down the circuit briefly, wrapping the electrodes for the ash to fall off, and then turning that back on and moving to a different section. In the SCR, it's creating some additional particulates by chemical reaction to reduce the amount of NOx in there, and so some of that gets captured by the precipitator as well. So the installation of the SCR increases the load on the precipitator some. And of course, you got to have that SCR's extra pressure drop, so we may have had to add a fan or beef up the ID fan to be able to get the air through it. Okay, so after the electrostatic precipitator, we're going to move into the wet flue gas desulfurization system, and there's different technologies that can be used. I think the most common is a bubbling type bed, where the gases, the blast on the ID fan is forced up through this bed that contains dissolved calcium. They used limestone. Uh, it dissolved a little limestone screen. They crush it up pretty good. Put it in the water. The the calcium dissolves, and then the calcium will grab onto the sulfur compounds, make CaSO4, which is a solid, and then that we can settle that out, get that out of the water stream. So there's a whole system that has to uh, keep that water chemistry correct, and then the gases pick up. They're essentially saturated when they come out of that bath, and then they are blown up the stack. So at Kingston, especially on a cold day, you see this white billowy clouds coming out of the top of the stack, and that's because they have scrubbers, wet scrubbers at Kingston, and so that's the water that as they picked up, those flue gases have picked up while they went through uh, that bath in order to capture the sulfur. And so then up the stack they go, and you see the cloud coming out. And some people call that pollution, but the pollution there is probably the CO2 and the small amounts of uh, other things that are not completely eliminated, but they're handled pretty well. So environmentally, these units do a pretty good job. Okay, let's see what else we can find to talk about here in some of these things, some of these slides. Yeah, this is okay. Let me rotate this around. It's pretty good. This one shows a comparison of a gas-fired utility scale boiler or steam generator. The steam book likes to call them, to coal-fired boiler. And so you can see that they're different beasts. Now, this gas-fired boiler is not really a Herzig. This is considered that we're going to just combust the gas and make steam compared to the size and scope of the coal-fired boiler. So it's the natural gas, because of the lack of ash, and it's pretty clean burning fuel, and you don't have the solids to deal with. So the spacing on the tubes can be much closer, and they can basically be much smaller. So you can see if you're going to build from scratch a natural gas boiler, it's going to be cheaper. It's going to be more compact. And natural gas is, a really good fuel, other than the fact that it's got the carbon in there. Methane is CH4, which is about 90%, 85, 90% of natural gas. And so, we still do put up some CO2, about half of the CO2 emissions from natural gas as we get from coal. So, and this is why the U.S. has reduced the amount of emissions of carbon. Our carbon footprint significantly in the last 10 years has been the advent of fracking. I think we've mentioned this before, but the more you use natural gas and the less you use coal, the more you reduce your CO2 emissions, as well as, certainly sulfur emissions, because generally speaking, there's not sulfur in natural gas. So natural gas is certainly a cleaner fuel than coal to use. It also, sometimes people will talk about wanting to retrofit a coal plant to natural gas. And it's not that it can't be done, but you can tell it's a different beast. And so there's just lots of issues in getting stuff out of the way, and getting you would have to change the burners, and this, that, and the other. So it's a matter of expense. It can be done. I'm not aware that it has been done very much in the past. I think because of the increased efficiency, if you want to burn the natural gas, you would just build a combined cycle plant, because this converted coal boiler would still not have a great efficiency. I mean, you might get 35, 36, 37%, but I'm pretty sure you would not get to 40. And that combined cycle plant can be in the mid 50s up to maybe even 60% efficient. So if you're going to spend a significant sum of money, why not spend a little bit more, or maybe a lot more, but get a much more efficient unit? So I think that's what's pretty well been done in the past. So let's pull on down here and see what we got. This is showing, just a second, let me flip them, rotate, and rotate. So this is an large industrial boiler, which, are certainly related. Probably not, maybe not quite as high pressure. We pick up a couple of components here. So we pick up a second drum. We pick up a a mud drum, a lower drum on the boiler, and we run some additional tubes. This is called the boiler bank. So, because typically what happens is we don't need as much superheat. So we put in more tubes to generate steam. So in this, we would be generating steam in the furnace tubes, and we would be generating saturated steam in the boiler bank tubes. And you see, we do have a superheater here, so we are putting out some superheated steam, but the emphasis here is on the amount of steam production, not on the amount of superheating that we do. So, it's going to vary depending on what the industry needs. But this drum is called the mud drum, and it's because any sediment or anything that can get in here, or anything that sloughs off the tubes, is anything fairly heavy is going to settle down to the mud drum. And so we do separate blowdown. We do what they call bottom blow, which usually comes from the mud drum, and headers that are down here on the bottom can also accumulate stuff. And it's common to blow those headers down ever so often, where you just have a valve and you pop that valve open for 5 or 10 seconds, and you get a pretty good flow out of there, but it's a short period of time. And so that flow hopefully is going to pull out any sediment that needs to come out of either the bottom of the headers or the mud drum up here. But again, this boiler bank are extra tubes to generate saturated steam. And then we show an economizer, and then we got some sort of a air heater, and then on out. So here's our FD fan blowing through the air heater and then into the ducting that eventually there's a primary air fan. And this is showing an overfire air fan. So that's just to distribute the air throughout the furnace for that stage combustion. Oh, this is showing a bark spout, so that you could inject bark or waste wood or something like that. So, you could be burning a combination of fuels on this thing. Yeah, pretty nice. Pretty good stuff. All right, I think that's roughly about 30 minutes. So I think I'm going to stop this now, get it posted, and send you another link to a video. So the combination will be about an hour and a half. So that will certainly cover one class. So we'll be back in touch later.